Okay, so let's recall some of what was said last time, or in my last lecture. So we'll always work on a closed symplectic manifold. And if you have some function, so time-dependent function on the manifold, which should be smooth. Let's say it's a non-degenerate Hamiltonian. I think, unless I get farther than I'm expecting, all Hamiltonians today will be non-degenerate. And I'll remind you what this means in a second. So of course this gives you this gives you a vector field. It gives you a time-dependent vector field x sub h. So in order to make some signs in formulas that will appear shortly work out better, I will use the convention that x sub h is defined by the property that includes into the first slot of omega as minus the differential of the function at that time. So I guess this t comma m goes to ht of m, and so that this should be a time-dependent vector field, which at any given time t has the property that it includes into omega as minus the space derivative of the function at that time t. And so this, of course, then gives you a flow phi ht. And non-degeneracy means that the determinant of the linearization minus the identity is non-zero at every fixed point, or phi h1 star. So at any fixed point, the linearization is, of course, an automorphism of the tangent space, and we ask that it not have 1 as an eigenvalue. Okay.
So you better write something.
Huh? Excellent. Thank you. Okay, so the question that was discussed last time is how many fixed points does VH1 have? And we addressed this by trying to do some sort of Morse homology on the contractible loop space, or to be honest, we did a sort of Novikov homology, as it would be called. So consider the space of contractible loops in M, and so we took some cover. So this is a certain cover which I defined last time. The details won't be too important for today. But a generic element of this cover looks like an equivalence class of pairs consisting of a contractible loop and a contraction of that loop. In other words, U is a map from the disk so that its restriction to the boundary is gamma. And so what Hamiltonian Floer theory is somehow it's Morse homology for the so-called action functional on the contractible loop space. And in accordance with this minus sign, I get a plus sign down here. So given a pair consisting of a loop gamma and a contraction of that loop U, I can integrate the form over the disk, and I can then add the integral from 0 to 1 of h of t comma gamma of t v2. Okay, and so we somehow do Morse theory for this, whatever that means. So all this gives us a chain complex, which as a set is defined as follows. So it becomes a little tricky on a generic symplectic manifold because you have to allow certain infinite sums in the chain complex. So the objects in the chain complex should be formal sums of critical points of a sub h. And as we discussed last time, what it means for gamma comma u to be a critical point of a sub h is precisely that gamma should be a one periodic orbit of this flow. Okay, so it's going to be some linear combination of critical points, except that it's allowed to be an infinite linear combination in a particular way. So in order for the boundary operator to be to actually land in here, one has to allow certain infinite sums, but the constraint is that for any real number c, so only finitely many gamma u's with action value at least c have coefficient non-zero. Or maybe another way of saying this is that what we're looking at here are potentially infinite sums of potentially infinite linear combinations of critical points where the action value on the critical point diverges to minus infinity. Maybe that's a more economical way of saying it than this. Okay, this is a module over a certain ring, which I wrote down at the end of last time, and the definition of the ring looks very similar to this. So this is called the Novikov ring. So gamma is the deck transformation group of this cover here. So that this is some ring, and its rank of this module is the number of contractible periodic orbits. Okay, so if you have a fixed point of this map VH1, you push it around by the flow and you get some circle. And this count. So because I worked on the contractible loop space here, this counts the number of those fixed points with the property that the circle you so obtain is contractible. Now I could have worked on another component of the loop space and I would have gotten a similar thing, but specific to that component. However, in any other component, the resulting homology would be 0, whereas in the component of contractible loops, the homology turns out to be the homology of the manifold. Okay, so that's what the chain complex is as a set, and the boundary operator on it. So it's supposed to count, formally speaking, it counts negative gradient flow lines. Of this function. So what are these? What do I mean by these? So these are solutions U going from the cylinder, R cross R mod Z, into M to a certain differential equation, du ds plus jt, so choose a circle parameterized family of almost complex structures jt, du dt minus x sub h is 0. So it counts finite energy negative gradient moments. Now, so in other words, so if I have a generator, gamma minus U minus over here, I look for solutions to this PDE that sort of are asymptotic at minus infinity to gamma minus. So here's a picture of one. Any such which has finite energy will be asymptotic at plus infinity to gamma plus. Moreover, so I have this disk here which capped off gamma minus. Well, I then join to that disk this cylinder, and that gives me a disk that caps off gamma plus. And so it determines another generator, gamma plus, comma U plus. And the coefficient of gamma plus U plus in D of gamma minus U minus is the number of cylinders that do this. So a key point is that this is, because this is Morse homology for an action functional, well, if this situation obtains, then the value of A sub h here is going to be higher than the value of A sub h there. So So the energy, at least for a solution to this, the energy would be defined as the integral of du ds squared, which is manifestly a positive number. So it's routine to see that if this equation is satisfied, so that the energy will be equal to the amount by which the value of the action falls along this gradient flow. So this energy is given by the change in the action value whenever you contribute to the matrix element. So d of gamma minus u minus is going to be some presumably infinite formal sum of critical points. And so what I'm writing down here would be, by definition, the coefficient on gamma plus u plus in d of gamma minus u minus. And whenever you have one of these cylinders that contributes to this, then its energy is given by this formula. In particular, the energy of any, if you have two different cylinders that contribute to this differential, then their energies will be the same. And that played a role just in defining the complex, but it also leads to an important feature of the complex, and so I'll start doing sort of new things now. So here's an important feature of this complex. What we have here is a filtration. So by the real numbers, I guess normally filtrations on complexes are considered to be over Z, but the natural thing here is by R. So suppose I have an element in my chain complex. So this is some sort of, this is one of these things over here. It's some kind of formal sum of critical points. Well, I will define the filtration level of this chain. Say L sub h of A to be the simply the maximal A value, capital A value of anything that appears in this sum. So A sub h, the maximal A sub h of gamma u, where little a gamma u is non-zero. Okay, so and observe that this really is a maximum, even though we're talking about infinite sums, because the A sub h's diverge to minus infinity, but they don't accumulate anywhere other than minus infinity, and so there is one single top, or maybe there's a tie, but there's a finite collection of top of highest levels that appear in this formal sum, and so the sort of filtered groups will simply be all those groups whose or all those elements whose filtration level is at most some number. So let lambda be a real number, and consider those elements of the chain complex whose filtration levels are at most that number. Okay, so this is the submodule consisting of things like this, with the additional property that all the A sub h's appearing here are less than or equal to lambda. Okay, so this is certainly a perfectly good subgroup. I guess it's not quite a submodule over all of this, but it's a submodule over a smaller version of this, and in particular it's a submodule over Z, say. But in addition to being a subgroup, it's a subcomplex. Why is it a subcomplex? Well, because of this fact here. when I hit anything in here with the differential, then I follow gradient flow lines downward. And, well, if initially all the action values were less than or equal to lambda, and then I follow the negative gradient flow down, then I land at somewhere where the action values are also less than or equal to lambda. So because this number is certainly always going to be non-negative, since it's the integral of a square, it will be true that the boundary operator restricts as a map CF lambda star of H to CF lambda star of H. So these filter groups are subcomplexes. They're preserved by the boundary operator. So, so you could say after this, it is a true observation. So we could then take the homology of the subcomplex if we felt like it. Namely, fix a Hamiltonian and fix a real number, and just take the homology of this lambda subcomplex, and you have the homology of a chain complex, and so you could think about that. Now, I'm putting this all down here, and maybe I should shrink the type or something, because I think it's better to resist the urge to pass to homology. I think one ends up learning more by trying to understand the chain complex itself rather than passing to homology at the first opportunity. But one thing that is different about this than, I guess this is the first time I wrote down homology. So the homology of this whole complex, as I discussed last time, is isomorphic to the homology of the manifold, and in particular is independent of H. Whereas it shouldn't be too hard to see that this depends on H. For example, if you add a constant to H, you just shift the filtration up or down, and so if you fix lambda and vary H, this is going to change. And so as I was starting to say at the end of last time, well, so we know that I guess I stated last time that you get, for two different choices of H, give rise to chain homotopy equivalent complexes, which is great because it allows you to prove the Arnold conjecture. But now that we've proven the Arnold conjecture, what else can you do? One thing you can do is you can try to construct invariants out of this that depend on H in a sensitive way, and so maybe that way you can learn something about properties that hold for some Hamiltonians and not for others. And the fact that this depends on H, and so certainly does the filtration, would seem to make it promising to try to understand properties that again hold for some Hamiltonians and not for others in terms of this filtration. Again, that said, I think this is the last time I'm going to pass to homology today. Okay, but at any rate, what we have is, for any given Hamiltonian, or any given non-degenerate Hamiltonian, we have a complex, and we have, moreover, a bunch of subcomplexes. We have a subcomplex of the big complex for every real number, and I propose to understand an individual Hamiltonian better by means of understanding what goes on with these subcomplexes. Okay, so I note here that D restricts to an operator that preserves the subcomplex. In fact, and this will actually play a pretty significant role in what I'm going to say for the rest of today, it does better than that. So the amount by which the boundary operator lowers the filtration level is given by this energy here. Now, I observe over there that this is clearly always a non-negative number. Well, unless duds is always 0, it's actually a positive number. And well, if duds is always 0, then it's not. Then what I'm going to get here is just some cylinder that sits at gamma minus forever. And in particular, it's not going to contribute to the differential because, well, for several reasons, among one of which is that the grading doesn't change. So so as far as cylinders that actually contribute to the differential, this is always non-zero, and this is always positive. And in fact, using Gromov compactness, you can see that there's a universal number that it always has to be, that this integral always has to be above, if it's not zero. So in fact, these are better than filtered. This is better than a filtration in the sense that there's some delta, which certainly depends on h, positive, so that the boundary operator restricts is an operator which lowers filtration by at least delta. And so again, this is better than better than the behavior of filtrations that one is used to. And well, I hope to convince you that this is a really useful fact. Okay. So as I said, my intention here is to elucidate properties that hold for some Hamiltonians and not for others by looking at the filtrations on these complexes. So it's about time to talk about what the Floer complexes for different Hamiltonians, how the Floer complexes for different Hamiltonians are related to each other. Are there any questions at this point? Yeah.
Does this mean that if you can somehow calculate each term of the spectral sequence, then you could get a kind of a sharp count of radial flows? Oh, sorry, periodic orbits.
You could. Maybe, but so in addition to not liking capacitor homology, I don't like to talk about spectral sequences. And so part of the reason for this is that so this is a filtration by R. So in the spectral sequence story, one starts with a filtration by Z and goes from there, and sort of the general construction of a spectral sequence does that. Now, of course, if you have a filtration by R, you can get a filtration by Z and run the spectral sequence machine. But unfortunately, so I don't really see a way of doing that, at least off the top of my head. So I guess that if you have a filtration by R, you just forget about all but a discrete subgroup worth of the value, or a coset of Z's worth of filtration levels. And
with the chain complex, can only change a discrete value of lambda.
Well, so
the subcomplex will change a discrete value of lambda. Is that true?
In this setting, no, it's not true.
Oh, okay.
That's what the problem becomes. Because so if I change the U here and fix the gamma, so how do I change the U? I glue on a sphere. Did I erase what the formula for A sub h was? The formula for A sub h is, well, it includes this term. So if I change U by gluing on a sphere, I change this term by the integral of omega over the sphere. Now, if the integral over, so one has a homomorphism from pi 2 to the reals, which, well, depending on what you're, obviously this homomorphism depends on omega, but it's quite possible that this homomorphism will have dense image. I mean, if it has rank at least 2, it has dense image if and only if it has rank at least 2. And so if it has dense image, then really you kind of have, you're not going to be able to separate things out discretely somehow, because I can. There will be somehow infinitely, between any two action levels, there will be infinitely many different new generators for the complex. So at least when this has dense image, you would be genuinely losing information by going to the spectral sequence. And so for that reason, I don't like going to the spectral sequence. And if you don't, probably some people in this room don't really like spectral sequences very much, so this should be good news. Okay, so I stated last time that that the complexes associated to different Hamiltonians were chain homotopy equivalent. I didn't really give any indication of why that was, but since understanding that is going to be important to understanding how the filtration changes, I'll pay that debt presently. So what do the Floer complexes of different Hamiltonians have to do with each other? So suppose I have two Hamiltonians, so let H minus and H plus be non-degenerate Hamiltonians. Well, the idea is to get a map from the Floer complex of H minus to the Floer complex of H plus by interpolating between the Hamiltonians, which you can certainly do. So let HS be a smooth, S varies in R, be a smooth family of functions. And so let's keep the interesting stuff in a compact region. So let's have HS be H minus when S is less than, say, minus 1, and H plus when S is bigger than 1. Well, the boundary operator involves just solutions to this equation where you have one H and you count these. And so we can modify this equation in a very straightforward way. So consider solutions to du ds plus j t, say, du dt minus x h s, at t comma us of t equals 0. Okay, so if these have finite energy, what's going to happen? So again, let's call the energy for the moment the integral of du ds squared. So if this is finite, well, so all outside here, the equation that this satisfies is the same as the Floer equation for H minus. And all outside here, the equation that this satisfies is the same equation for H plus. And this is an infinitely long end. So it should be plausible, at least, that more or less for the same reason that finite energy things over here are asymptotic to periodic orbits, that likewise finite energy things here should have to be asymptotic to periodic orbits. So I mean, if it weren't the case that for S extremely negative, this were asymptotic to an orbit of U minus, of gamma minus, sorry, or of H minus. If it weren't the case that this were asymptotic to an orbit of H minus, then this would stay away from 0. And so, since you have an infinitely long end, then this would be very unlikely to have finite energy, and likewise over here. So what's going to happen for any finite energy solution is that there's going to be, just like before, there are going to be orbits that this gamma minus on one end, gamma plus on the other end of the respective equations that this will be asymptotic to. So there will be gamma plus minus. So these are periodic orbits Well, at minus infinity, the equation is the same as the equation for H minus. At plus infinity, it's the same as the equation for H plus. So these are periodic orbits of respectively H minus and H plus. So that you approaches them as s goes to plus or minus infinity.
Analog to what you're doing in normal Morse theory? I mean, like two Morse functions and your counting flow lines go from critical point to one to critical point to another.
Yeah, absolutely, you could do that.
It makes sense in that.
Yeah.
As well.
Yeah, you can perfectly well interpolate between the two Morse functions, and you get a map from one Morse complex to the other. And yeah, that's worth thinking about doing. Okay, so, well, I just said that I was proposing, I just announced for the first time that I was proposing to use these to make a map between the complexes. Well, okay, so let's suppose, again, we're supposed to think about sort of capping disks. So, so here's U. So if I cap off the minus orbit with a disk U minus, and then that induces a capping for the plus disk by say U plus. So if U plus is the thing that you get by attaching U to U minus, well, so a not difficult calculation shows the following. So,
U is the second minus.
Oh, yeah. Okay. So you can do the following calculation. So over here, so the Floer complex of H plus is Morse homology for this complex. The Floer complex of H minus is Morse homology, or is Morse homology for this function. The Floer complex of H minus is Morse homology for this function. And well, you get minus the energy. So note that in the analogous formula that I wrote down earlier, these two are switched. So switching them back picks up a minus sign. And well, the other thing that you get if you run through the calculation is just the partial derivative of these HS's, which are varying with s, though they're constant outside this compact interval. Just the partial derivative evaluated at t comma u of s comma t ds. Okay. Now, I guess there are there are lots of choices you could make for h sub s. Somehow the most economical one would be to just sort of interpolate between h plus and h minus. So let's, just for definiteness, let's say that hs is beta of s times h plus 1 minus beta of s times h minus, where, say, beta is some kind of plateau function. So it's 0 out here until you get to minus 1, and then it rises to 1 here. Okay, so if, assuming I did it right, if when you're at s less than minus 1, you get h minus. When you're at s less bigger than 1, you get h plus. So this is a picture of beta.
Obvious that you get the negative sign over there.
I'm leaving it to you to do the calculation. It is an instructive exercise to do this calculation.
So from one to the other, so it might not be always going down. Is it always obvious that?
So because of this term, it doesn't quite necessarily go down. But okay, so suppose that h plus were h minus. So this would be sort of the same formula that I wrote down. So if h plus were h minus, then HS would be independent of S, and so this wouldn't be here.
Right.
And so this is saying, in that case, this is saying that at the end of a negative gradient flow line, I'm further down than I was at the start, which should sound right.
Okay.
Right, on a negative gradient flow line, the function decreases. Now, but if I want to go between different functions, I get this extra term here. Well, so having made the sort of most economical choice of H sub S, so this is minus E of U plus the, well, let's switch the, do I want to switch the, not that it matters, but, so
you add the terms so that you get the negative sign over there, right?
I mean, so there's a formula for this, and there's a formula for this.
Right.
And then you use the fundamental theorem of calculus, or something. Or maybe you don't even do that.
Okay.
You use the definition of, you use the formula for this, and the formula for this, and the definition of a Hamiltonian vector field. And you do some manipulation. I'm not going to do this for you. You can do it if you're interested.
Right. Okay, I'm okay.
Okay, so DHS ds is just beta prime of S times H plus minus H minus, if I did that. Did I do that right? Yeah. Of T comma U of ST, ds dt now. So, well, I can look at H plus minus H minus and ask what the largest it ever is, and I get some bound here. And then of course the integral from minus infinity to infinity of beta prime of S is just 1. And so if I bound this by the largest this ever is, I can then take it out of here, and I get minus E of U plus the integral from 0 to 1 of the maximum over M of H plus of T dot minus H minus H minus of T dot dt. Because I integrated out beta prime because that's what this is. Okay, so I claim this is useful. So first of all, this implies that if I fix this and this, well, so this is just some number. Let's give this number a name. Let's call it. Let's call this eta of H minus H plus. So this is just some number that I can look at the two functions and see what it is. If I fix this and I have this fixed number, then this says that I get an energy bound on U. Okay, and so we can apply compactness and see that the Gromov compactness and see that the space of these is compact. And so in view of that, that makes it feasible at least to define a map. Say phi H minus H plus, going from the Floer complex of H minus to the Floer complex of H plus by, I'll just, because I discussed extensively yesterday how to do this in general, I'll just say by counting isolated solutions to this equation, which, like most equations, is named star. Okay, and by the way, because unlike in the case of the Floer boundary operator, there isn't a free action of R here. What I'll want to count is index 0 solutions, and so this will preserve the grading for whatever that's worth. So, what does this do to the filtration? So, with respect to these filtered groups, so if I start out with something at filtration level below lambda, then the filtration level that I end up at the end, well, is going to be less than or equal to lambda minus whatever the energy is, and the energy is a non-negative number, and then plus this number, eta h minus h plus. So this ends up at CF lambda plus eta h minus h plus of h. Okay, so these are called continuation maps, and they we have good control over how they affect the filtration. Okay, so we can just stare at the functions and see what this integral of the maximum of h plus minus h minus is, and we're guaranteed that what this will do to the filtration level is it will increase it by no more than this number. Okay. Well, of course, there was no there's nothing sacred about what I call h minus and h plus, so I can do this in the other direction, and I get a map phi h plus h minus defined in exactly the same way, just apply a 180-degree rotation to all the pictures, going from CF lambda of h plus to CF lambda plus, well, eta h plus h minus of h minus. Okay. Yeah.
One thing I don't quite understand is your eta of h minus h plus. Does it actually depend on the path that you choose from?
Yeah, it will. So I guess it does somewhat, but if I decided to get more specific and say let's do this in the most economical way possible, which is to just have something like this that interpolates between the two. If I were less smart about the path that I chose, then I wouldn't get as good an eta. That's definitely true.
I wouldn't say this is the most economical. You don't know.
Actually, yes. Assuming I'm not running way over, pretty soon we will see an example where there's a much better one. But okay, so somehow maybe the most obvious and plausibly the most economical. But if you notice something else in particular cases, it's maybe not the most economical. That's true. Yeah. So I mean, everything you're going to do depends on choices, and for that matter, I mean, this map depends, strictly speaking, depends on the choice of an almost complex structure, which I'm suppressing, and things like that. But it is definitely the case that you can get maps that do this that do this to the filtration. Okay, well, so of course if we have two maps we can compose them, or if we have two maps with matching codomains and domains we can compose them. So if I compose them, if I go from h minus to h plus first and then back to h minus, I evidently get a map from the Floer complex of h minus to itself. And what does this do on the filtered groups? Well, so if I start at filtration level lambda, I add at most eta h minus h plus here, and then by lambda there, and then to that I need to add at most eta h plus h minus. Well, so notice that eta h plus h minus plus eta h minus h plus. Well, so what do? For any given time, I take the maximum of h plus minus h minus for this one, and for the other one I'll take the maximum of h minus h plus. And in all, what one gets is the maximum over m of h plus minus h minus. Minus the minimum of h plus minus h minus, because minus the minimum of h plus minus h minus is maximum. Okay, so this has a name. This is called the Hofer norm of h plus minus h minus. So this is I'm integrating over time the total variation of this function. Okay, so when I start at filtration level lambda, I potentially add eta h minus h plus, and then likewise here I add eta h plus h minus. Okay, and so I end up at filtration level at most lambda minus plus the Hofer norm of the difference between the two. Okay. So as it turns out, so part of the reason why Floer homology is independent of the Hamiltonian is that this is chain homotopic to the identity. And, well, I claim that it is profitable to find out why it is chain homotopic to the identity, and moreover look at what the chain homotopy does on the filtration. So why is this so? So consider it just as a map on Floer complexes, on the entire Floer complex. So really what this does is so somehow I start out at h minus, and then there's some blurry place in the middle, and then I end up at h plus, and then so that's this map, and then I compose it with the second map, which starts at h plus, and then there's something that goes on the middle, and that turns me into h minus. So there's some sort of gluing result that implies that this composition agrees with a map that I'll express diagrammatically with the following picture, which hopefully will make some sense to people. So take some large number R, and basically put this picture over here. So I'll have h minus here, and then I'll have h plus in the middle, and then, sorry, that should be minus R. And then R over here, and sort of put this picture over on this side, and somehow glue them up in the middle. So h minus, h plus, h minus. Okay, so then the point is, if R is large enough, somehow I can paste solutions here and here together to get solutions to the thing that corresponds to this diagram. So this is representing some sort of continuation type map that starts at h minus and ends at h minus. And of course, there's another way of getting from h minus to h minus, which is just to stay there the whole time. So here's another way of getting from h minus to h minus. And if I interpolate between these two, so maybe at halfway through I would have minus R, R, and I'd have h minus over here, and I'd have the average, say, between them over here, and then I'd have h minus over here. So I could take some continuous family of these homotopy maps and sort of homotope this stuff in the middle down to exactly h minus. Okay, so this picture is supposed to gives rise to this map. So this picture gives rise to the identity. And so somehow you'd like to deform this map into the identity. Now, okay, so here's v h minus h plus, compose v h plus h minus. So you have some solutions over here, and then here's the identity, and you have some solutions there. And you'd like to go across and say that, and join up this and this. Well, so I mean, maybe that works out, and maybe there. So consider all the things that you get in some one-parameter family. So maybe there are isolated components, and and maybe this goes to that. But there might be some non-compactness at various points. So maybe that goes to that, and that somehow drifts off to the boundary side. So what's represented on the boundary? Well, so at least somehow generically, and I'm suppressing all the technicalities about how you can set this up so that it honestly works. So the way that this could go wrong is somehow you could get sort of a trajectory that breaks over here, or a trajectory that breaks over here. Now, generically, the only thing, so these places where this cobordism argument breaks down will correspond precisely to one of the two following pictures. So remember, on sort of the infinite ends here, I always have H minus. So what I could have is something that contributes to the boundary operator for H minus. So somehow something like that could escape over on this side. And then follow that up by basically an index -1 solution to this equation. Or likewise, you could do it in the opposite direction. You could have a boundary thing escaping off to this side, and then have an index -1 solution over here. Now, of course, for any fixed time, that's not going to happen generically. But since we're doing a one-parameter family of these homotopies, it occasionally will happen. Okay, so just to be brief about it, so you can define a map K from CF. So this will be a degree -1 map, or sorry, a degree +1 map. So the boundary operator has degree -1. From CF star of H to CF star of H, and so somehow it should count index -1 solutions that arise during the homotopy. And, well, for basically the same reason that this original map only raises filtration level by at most the Hofer norm of the difference, likewise, on any of these, the action is only going to increase by at most the Hofer norm of the difference. Yeah. I mean, so maximum minus minimum as well as positive. Okay, so restricting to the filtered groups, K maps CF lambda of H minus to CF lambda plus Hofer norm of the difference H minus. And I guess I keep on alternating the. Okay, and then so this is supposed to be evocative in some way. So over here I have the composition of these two maps. Over here I have the identity. Somehow this is counted, I guess, the way I did it. You would have K first, and then you would have D, and this is counted by DK. DK. Okay, and well, so somehow we have these various maps that count things that arise on the ends of a one-dimensional moduli space, and this is supposed to be all of the boundary, if you believe that. You get that phi h plus h minus compose phi h minus h plus minus the identity is equal to dk plus kd. Okay, so most of this is old news, but somehow I think it's only recently been appreciated that it's worth really paying attention to what all these fundamental maps do on the filtration level. And to give evidence that that this is fruitful, I'll state the following, which I don't think even deserves to be called a theorem. I would call it a corollary of these standard constructions. So this, so I guess Cornet and Ornitzky observed this in the aspherical case, using a somewhat different argument, and then I did this in general using the argument that I'm presenting here. Okay, so let's say I have a non-degenerate Hamiltonian. H. Then there's some delta H, which is the same one that I wrote down before, so that if I take some other non-degenerate Hamiltonian, H prime is another non-degenerate Hamiltonian, and the Hofer norm of their difference is at most this number delta sub H, then the Hamiltonian vector field of xh prime has at least as many one-periodic orbits as the Hamiltonian vector field. Contractible, let's say. But actually, I don't need that, but I guess to stay within what's been said, I should say contractible, as does xh. Okay, so if I start with a Hamiltonian and I perturb it, so a Hamiltonian function, just the function, and I perturb it, well, if I perturb it in the C0 sense by this number, then I will get at least as many periodic orbits as I had before. Now, I claim that this is sort of odd. So, also, and actually, I mean, I could just as well say fixed points of VH1 because you can do this for any homotopy class. So, I mean, so if I start with a diffeomorphism that's, say, transverse to the diagonal, and then if I perturb that diffeomorphism in a C0 small way, so sorry, this doesn't make any sense. So this is the graph of some diffeomorphism, and this is the diagonal. So if I start with a diffeomorphism, like the time one map of a Hamiltonian flow, and I perturb the diffeomorphism in a C0 small way, it's easy to see that you have at least as many fixed points of the C0 perturbed diffeomorphism than you had before. Because, I mean, basically what can happen, well, at least assuming the fixed points are non-degenerate, at least what can happen is, well, so maybe the C0 small perturbation sort of introduces some wild oscillation in the diffeomorphism, and that might introduce more intersection points with the diagonal in M cross M, but there's no way that I'm going to be able to get rid of any of these fixed points. So sort of by local arguments, and you could make this precise using the Brouwer fixed point theorem or something, you can see that a C0 small perturbation of a non-degenerate diffeomorphism has at least as many fixed points as the original one. However, to make VH prime 1 C0 close to VH1, one would need, so how do you make these diffeomorphisms? The first thing you do is you differentiate the function. So to make the diffeomorphism C0 close, one would need H prime to be C1 close. to h. Okay? But here I'm actually showing that if just this generating Hamiltonian is C0 close, then I still preserve fixed points, which I think is so I'll show in a second how to prove this, but I don't. It seems like this ought to be somehow an elementary statement, but I don't know a way of proving it without Floer theory. And actually, I mean, there's an analogous statement just for Novikov homology of forms on closed manifolds, and I don't know how to prove that without Novikov homology. So start with a transversely vanishing closed form on a closed manifold. If I perturb it by d of a C0 small function, which is C negative 1 small or whatever, I preserve, I have at least as many fixed points as I had before. I don't think that's intuitively obvious at all. And in fact, if you drop the assumption that the form is closed, it's not true. Okay. The point is that the boundary operator for the Floer complex of H minus, or of H, lowers filtration by at least delta H. Okay. Now I'm assuming that I perturb H to H prime, which has Hofer norm differing by at most delta H. So, okay, so let's have epsilon be delta H minus the difference in the Hofer norms. Okay, so I guess I need to switch indices. So phi H, the second.
You wrote plus over there again, no?
No. The boundary operator decreases filtration level.
Okay, right.
The boundary operator decreases filtration level. So this is a minus sign. Over there I have plus signs, but the minus sign is going to win. That's the point.
Okay, right.
Okay, so I have this equation translated into H's and H primes, which says that, well, I'll write it this way, that the composition of these two maps is the identity plus dk plus kd. So let's call this whole thing A. Okay, so the boundary operator decreases filtration level by at least delta H. K increases filtration level by at most the difference in the Hofer norms. So A decreases filtration level by at least epsilon, where epsilon is the difference between those two numbers. Okay. Well, now we remember what we teach our calculus students. We teach our calculus students about the geometric series. So let B, okay, so I claim that the following makes sense. Okay. So minus A to the n apparently is going to decrease filtration level. So this decreases filtration level by n epsilon, which of course diverges to infinity as n goes to infinity. And in view of that, so remember what infinite sums we were allowed. We were allowed infinite sums where the action values diverge to minus infinity. And because we are allowed such, a moment's thought shows that this actually is a perfectly valid endomorphism of the Floer complex. Okay, so because of this map is well defined. So I don't know, let's call it B. Because it will be true that when I try to apply this to some given generator for the complex, the result of it will only have finitely many terms above any given action level.
So because of that one, the k plus k delta,
Yeah.
one increase mode to.
Yeah. So D decreases filtration level by more than K increases filtration level. Okay. So the result is something that decreases filtration level by a definite amount. Okay, so this thing is well defined, and of course, what we teach our calculus students is that if I compose this with that, I get the identity. That's about what we teach them, right? So B composed B H prime H composed B H H prime is the identity. So what does that tell us? So that this is an injective map. Okay, and so why does that help? Well, remember that, so, I guess BHH prime is some map that goes from CF star of H to CF star of H prime. And it's a module homomorphism. And, well, so the things whose counts I am comparing over here are precisely the ranks of these two things over the Novikov ring that I mentioned earlier. So since the rank of H prime is at least the rank of the four complex of H, what I said over there immediately follows. How much time do I have?
Less than 5.
Okay.
Here you use the fact that number of rings is PIU. I mean, number of generators.
I'm not sure do I even use that?
Yeah, if you have 3 modules, finite generated 3 modules
Yeah.
over some ring.
Oh yeah, okay. So I need to, so I guess the algebraic fact that I use is that an injective map of modules over a ring, finitely generated modules over a ring,
Rough is,
increases the rank.
yeah.
And you need PID for that? Okay. I believe that. Okay, so I guess in the remaining time I want to point out something else that the filtration buys you. So if I have some Hamiltonian, so it determines a path. In, well, I guess I haven't used this notation before, but the group of Hamiltonian diffeomorphisms. So of course, this gives me some element of the universal cover, which is identified with the group mod homotopy RL endpoints. Okay, so suppose I have two Hamiltonians that represent the same element here. So their induced paths are well, they have the same time one map, and moreover they can be connected by Hamiltonians that retain that property. So suppose H plus and H minus represent the same element. Okay, so what that means then is that, well, it's easy to see that what it implies. There's a little subtlety with the circle here rather than R here, but it's an exercise to see that one can still do this. So there's a family HS of Hamiltonians, smoothly varying in S. Let's say HS is H minus for S less than minus 1, H plus for S bigger than 1, so that all the time one maps of these are the same independently of S. Okay, so somehow I have a square in the so at any given S value, I have a particular Hamiltonian path. And their time one maps are the same, so I have some sort of square in the Hamiltonian diffeomorphism. Okay, so let's assume. So I may as well assume that that these are normalized. In other words, the integral of h plus minus of t at any time with respect to the symplectic volume form is 0. If it's not initially, I can just subtract off some time-dependent function, and it will be. So also, at least I can choose the HS's to have the same property. Okay, so the derivative with respect to t of the Hamiltonian diffeomorphisms that are induced by these various functions h sub s are by definition the Hamiltonian vector fields of the functions. However, I guess I think it was Banyaga who first noticed that that if you have a path in the Hamiltonian diffeomorphism group, it is induced by a Hamiltonian vector field. That's Banyaga. So I have these diffeomorphisms phi h t, or phi h s of t. In other words, the time t flow of the Hamiltonian hs. So define the vector field yst by d by ds. So differentiate with respect to s of these diffeomorphisms. So I guess that means this. Okay, so Banyaga noticed that these are Hamiltonian. All right, so they're Hamiltonian vector fields. Of some functions, let's say kst. Okay, so now I have this homotopy. I have this path that goes from h minus h plus here. So I could define the continuation map just like I did before. But actually, there's a better way. There's a more economical way, as Youngin would say, of defining a continuation in the presence of this. So I can define a map. I'll still call it phi from the complex of h minus to the complex of h plus. By instead of counting what I did before, I'll count solutions to a slightly modified equation. I'll subtract off the Hamiltonian vector fields of this from the du ds part, and then still do the j du dt minus xh s equals 0. Okay, so I learned this trick. Learned this trick from a paper of Ellie Kerman. Now we used it for something a little different. So the great thing that happens is that when you modify the continuation equation in this way, it works out. So, well, I guess another thing that Banyaga showed is that it's key in deriving the following: dHds is k dt plus the Poisson bracket of h and k. And somehow, using this useful expression, it turns out that that when you compare what's at the end, what you get at the end, or the action value of what you get at the end, to the action value of what you get at the start, Well, you just get minus some version of the energy, minus the squared norm of this thing here. Okay? So the exercise. But of course this is non-negative, so it's non-positive.
I couldn't quite understand the subscript of pain as
ST, yeah. Okay, so these are the Hamiltonian vector fields of certain functions. So denote those functions by KST.
Okay. Right.
So differentiate this with respect to S. This gives you a Hamiltonian. This gives you a vector field of some kind that depends on S and T. So it turns out, as August noticed, that these are the Hamiltonian vector fields of some function. So this is what they are. Okay, so consequently, phi actually maps the lambda filtered group of H minus to the lambda filtered group of H plus. There's nothing I have to add here. So I guess the basic fact is that using an argument very similar to what I gave before, so I can construct the same map back and look at the chain homotopy between them, so that so you get that phi is an isomorphism. And again, this well, you use the same sort of geometric series trick that I did before. Okay, so thus. So I guess just to sort of summarize the lessons of.
Actually, can I ask one question?
Yeah.
I think this is true only when this path phi th itself lives in the two-part family in the Hamiltonian deformation group.
Yeah, it does, doesn't it? I mean, in the setup.
So it is not clear. You mentioned that. What is that? Oh, phi t. So what is the hypothesis?
Okay, so I have two. So basically, I have an R family of functions HS, constant over here, which all induce the same time one map.
Oh, okay.
Okay, so I guess sort of the lesson of the first talk was that if you have a symplectic manifold M, you can construct so you can make some choices. So you can choose a Hamiltonian. Plus some other data, and you get some complex with chain homotopy type independent of the various choices. Okay, I guess there were more lessons than that, but that's one of the things that comes out. So this is saying that if you have a sort of non-degenerate element of the universal cover of the Hamiltonian diffeomorphism group, you can choose a normalized Hamiltonian. These all do need to be normalized. I guess that's another hypothesis. Okay, 1 minute. Okay, choose a normalized Hamiltonian. Representing this element. And of course you make some other choices like an almost complex structure and stuff. And the output is a filtered chain complex So it's uniquely determined up to isomorphism of our filtered chain complexes. Okay, so an element of the universal cover uniquely specifies an isomorphism type of filter chain complexes. And by isomorphism, I mean in a very strong sense that you have a chain map which induces an isomorphism on the level of groups for at all filtration levels. And so philosophically, that suggests, though to say it this way is maybe a little anachronistic, that says that if I want an interesting invariant of something in the universal cover, I should think algebraically about what invariants I can cook up out of sort of isomorphism types of filter chain complexes, and that'll be an interesting invariant. And I'll talk about one of those tomorrow.
Any questions, please?